So let us continue by exploring data, and this in this module we will have a look at mostly at principal component analysis, but it's still about how to explore data. So this week's content, data dimensions. I have to say a few words about this because this is really important now. Then the principal component idea. What is this, and how do we? What is the sort of the thinking behind it? We will do some PCA and then look at the output we get, the explained variance, the loadings, and the scores. And these are the things we typically plot. We make figures, plots of this. Small look into the mathematics behind PCA, very little though, but it's nice to have seen a little bit of it to understand some of the details here. We have to say a few words about scaling or standardization of data, because that really may have a huge impact on the outcome of a PCA. And finally, I will also add a little bit about something called multidimensional scaling, which is sometimes also referred to as principal coordinate analysis, which is, as you can hear from the name, it's very close to PCA, but slightly different still, and an alternative that pops up now and then. So at least you should have heard about it. I think it's not a big thing here. The big thing is PCA. So PCA you can read about in chapter 5 in the R book, if you like. That's where this is mentioned in that book. So, as I said, data and dimensions. We need to say a few words about this. And typically we have a data set, a table, where we have n rows and p columns, right? N observations or data cases and p variables. That's something we talked about last week as well. So each row or data case we can now imagine is a point in a p-dimensional space. And notice it's p because we have p variables, right? P columns. Each column is a new coordinate, you could say. So each variable is a coordinate or an axis. And of course this is most easily visualized if you have only 2 or perhaps 3 axes. When we have like 10 axes or 10 variables, right? It's very difficult to sort of see that this is in a 10-dimensional space, but it is. We cannot visualize it, but we can still think in the small dimension world, right? And that's what we will do here now. So here we have one variable, and as long as we have only one variable, the points are sort of located along one axis, so like this, right? And you can see them here. Point 42, where is that? That's this one, right? Point 42. Point 69, yeah, that must be this one. Point 15 is probably the one to the left here, right? No, that's point 12 is the smallest one. 12 and 15, they are here, yeah? Okay, so this is a one-dimensional situation where you have only one variable, and we can actually mark the values along one axis, right? If you add so that you have 2 variables, then we will need a coordinate system consisting of 2 axes, right? The V1 axis is horizontal, the V2 is vertical here, right? And now again, each point is also each row here, each data case corresponds to a point here. So for instance, the first one here, point 42, point 99. Yeah, that's this one, because it's point 42 down here, point 99 over here. So each row here has a number of coordinates, and if you look along the first axis, the V1 axis here, the V2 axis there, and so on, you will locate all of them. And the same if you have 3 variables, we can still somehow make a figure, right? A 3-dimensional plot then with V1, V2 and V3. So we have the third axis. And this is actually where it stops for us, right? A four-dimensional table now, a table with 4 columns. We have big difficulties in making that into a figure. And not to mention if we have like 10 or 100 or 1,000 columns, it's hopeless, right? But even if we have 1,000 dimension, 1,000 columns, we can still sort of think of each data case here as a point. It's just that it's in such a high dimensional space that we cannot really visualize it. But it's there, right? And we see the data points. We see the values, right? The data, the coordinates for each row here. So many variables means a large P, right? And that's what we call multivariate data. And that's what we will deal with more or less in this course, right? Sometimes we have quite many, and sometimes not so many columns, but this varies a little bit. It would, however, be nice if we could plot the data and see how the data cases are located relative to each other, also in the case where we have more than 3 columns, right? And that is exactly what we are trying to do now in PCA. So the dimension reduction is what we are going to do. Can we actually sort of compress the data in some sense, so that we can use a low dimensional, for instance 2-dimensional view, and still see, if not all of it, at least the majority of the information in the data. Is this possible? And that's actually the idea that we will try to pursue now, and use principal component analysis or actually multidimensional scaling for doing that. Right. So even if we have high dimensional data, we want to try to plot them in a meaningful way. That's explorative data analysis. Centering the data. Yeah, this we talked about also last week at the very end of last week's talk, but let me just repeat it. So centering the variables means for each column 1, 2, 3 up to P, compute the mean value of the column, and then subtract the mean from all values in that column. So you do this for each column separately, right? The first column, a mean value, subtract it from all the values in the first column. Then go to the second column, compute a new mean value, subtract it from all the values in the second column, and so on, and so on, and so on. And the point is that this centering does not change how we observe data cases, how they are located relative to each other. And we also briefly saw this last week, but we will do that again now, because centering is really the first thing we do in a principal component analysis. So that's always there, you could say. And that's why we have to sort of repeat this a little bit here now. So we always center the data when computing a PCA. We will see shortly that we don't sort of explicitly do the centering ourselves, because the function in R that do the PCA will also do the centering for us. But this is important to realize, that the data will be centered, right? So when we inspect them after we have done the PCA, we need to understand why they are also sort of centered around 0, you could say. So this is the default behavior in R. You can actually turn it off, but that makes little sense, because then you just waste one principal component doing the centering. So let's jump to an R session and have a look at how we do this. Okay, let's have a look at this first R session here. And what we do here is simply to simulate some data. So let me first copy this code here. And then I go back into RStudio and I make myself a new R script now. So, and I paste it into here, and I save this as week 4 script. like this in my STAT340 folder. So we simulate some data. This first statement here is just to set the random generator for R. R can generate pseudo-random data, as we call it. And if you want to be sure that the exact same data are generated each time, you have to fix this seed, as we say. If you don't do this, it will still work, but then the data will change every time you run the code. And you will not get exactly the same picture as I get here now, so that's why I chose this, to get exactly the same picture each time. So let's run this. And then we sample, here I create sort of what I could call a mother variable, x. And then I simulate the data. So I have 3 columns in this data set. x1, x2, and x3 I call them. Silly names, but this doesn't mean anything. These are just random numbers, right? And notice here that the first 2 columns is actually this x plus some random noise. And x2 is also the same x plus some random noise. So x1 and x2 are 2 columns that are very similar to each other, we would say, right? They will be very correlated because they basically contain the same sort of core of information, but they are slightly different because we add some noise to both of them, and this noise is different from them, right? So if we run this here, we will have this data table. We can look at it. So now we have 3 columns, right? And x1 and x2, you can't possibly see that they are right here. They are both negative, right? Here they are both positive. Here they are both negative again. So they are sort of correlated, right? A little bit. While this third one is very different from the other 2. So let's go back here and do some plotting. And here I use our package called plotly. And you have to install that package if you haven't to run this, because this will give will produce 3-dimensional plots. ggplot is not very good at that. So let me just load this package. And then I plot here, and I won't go into the detail of the code here, which is not important. The important thing is what we see. So now you can see we have a 3-dimensional space here where all the points are, each point here now is a dot here, right? And since we have 3 columns, this is all the data we have sort of in this 3-dimensional view here. And the nice thing about this is that you can now use your mouse to look at this from different angles. And that's really the big point here now, because notice now that this is the view we get if we plot x1 against x2, right? And now x3 isn't it x2? No, this is actually x3. Yeah. Can you see? x3 is up here now, x1 here, and x2 is the one which is in through the depth of this picture, right? You can see x2 up there, x2. So you can now look at this from different angles, right? If I look at this like this, you will clearly see that. So now we see the x1, x2 image, you could say, right? x1 is down here, x2 up here. And we can see these 2 are correlated, right? Because it's when you have small values of x1, no, sorry, large values of x1, you also have large values of x2. The axis is upside down now, but anyway, you can see the values on the axis here, right? x2 goes from 0 down to 10, 12 here, and x1 goes from 0 to 10, 12 here. The point is, however, that if you look at this data swarm, it's like a swarm, right? If you look at it from this angle here, then it looks almost like a ball, right? Can you see that? But if I turn it and look at it from this side, now we can see there is a very long distance between those points out here and those points to the left here, right? So the spread or the variance in this data is very different depending on along which axis you measure it, right? And how from which angle you view the data. And that's really the essence of PCA that we will come to shortly. So let's have a look at the centered data then before we finish this session. Let me copy this code and paste it in here. So now I create another data table. I call it data2 table, right? Which is the original data table, but I now mutate each column. And I say the x1 should now be the sort of the old x1 minus the mean of that old x1. That's what I call my new x1, right? And the same for x2. The new x2 is the old x2 minus the mean of the old. So this is centering, right? This is centering. And the code line here that I commented out, this is just how you can do this centering using a function in R called scale without actually manually doing this, subtracting the mean. This will do it for you. If you call it with center equal true, it will do centering. So it will result in exactly the same. Let's run this line of code and have a look at the data table now. And the only difference now between data table, the original one, and the new one is that the mean value in each column is now 0 in this here. While in the original one it was not exactly 0, at least. It was perhaps not very far from either, but regardless of how the original data were looking like, the new data table has values where we have exactly 0 as mean value. Let me demonstrate that. Let us compute the mean value for data table x1, the first column in the original data table. What is the mean value in that column? 4.81, right? But if we do exactly the same for the second data table now, yeah, it's not entirely 0, but and this has to do with some rounding off errors, right? It's 6 point something times 10 to the minus 17. Right? 10 to the minus 17. So it means it's 0 point and then 16 zeros, right? And then 6 something. So this is very, very close to 0. It's just a rounding off error, this. So it's essentially 0. And that's the same for the other 3 as well. So when we do the plotting of this data now, we do exactly the same plot, but we use this new data table instead. And let's have a look at that one. And notice now that the shape of the cloud has not changed at all. What has changed here is where you find the origin of the data space. So now you can see this axis, the x1 axis, goes from minus something to plus something, and 0 is in the middle. And if we look at the x2 axis over here, you will see exactly the same thing. It goes from minus something here to plus something here, and 0 in the middle. And the same goes also for the third axis, the x3, right? You see the 0 here in the middle, positive and negative. So everything is now sort of distributed around the origin of the coordinate system. But the shape of the data swarm is really the same. If you go back to the previous plot and look at that one, it's exactly the same swarm. It has just been shifted to some other location. It's now centered around the origin, but relative to each other, the points have not changed their location. So this is illustration of centering of the data does not sort of alter the relative position of the data points. So let us now turn to the PCA model and see how is the idea behind principal component analysis. Well, the idea is to try to decompose the data variation in the full p-dimensional space into two sources. And we can write it like this. The full variation equals what we may call signal plus noise. So, and obviously signal is what we are sort of looking for. This noise part here is not so interesting. So this is sort of the main idea. There are sort of two sources of variation. One is signal, the other one is noise, and it's the first one we are interested in. So that's the important variation in a sense, right? And it's reasonable to assume that if you have large variations in your data set, this is due to signal. This is due to signal. It's the big variations, right? Because if the big variations were noise, then it just means, because this is relative, right? Then it just means there is no signal here, right? It's only noise, right? And the signal is sort of not random in a sense. It's real information, right? Or real correlations, or real variations in the data. And the randomness, which occurs mostly in the noise, has a tendency to distribute along all axes the same way. So the point is that this signal part is hardly ever filling up all the p dimensions. It's not like all variables are important in a sense, contain signal. So it's a dimension q which is smaller than p. How much smaller we don't know, and this depends on your data, but as a general way of thinking, we say that okay, there is a smaller dimension q, smaller than the full dimension p, which is sort of containing this signal part. The noise is unimportant variation, and the noise is sort of distributed along all the dimensions. So also among this first q there will be some noise, but the point is that this smallish noise variation you find in all dimensions. So yeah, so it's random, or at least we can we usually think of it as random. It doesn't necessarily have to be random, but from our sort of viewpoint, it looks random, right? And it spans, as I said, all p dimensions. But it's typically is equally much present in all dimensions, while the signal part is only present in some dimensions and not at all, you can think of, in the rest. So we can also make it sort of a graphical view of it like this, where we have the full data set here with all the p variables, right? And we can then decompose it into the signal part, which contains only a q variables here, right, the smaller part, plus the noise, which is equally sort of abundant in all dimensions. So the gray data here is partly due to the black signal and partly due to the whitish noise, right? And the trick now is to try to decompose here, right? So that from the data set, this is the data we have. We want to sort of try to recognize these two parts and then focus only on this one. So the principal components. The first principal component, how do we find it? Well, find some direction in this p-dimensional space. Project all data points into this coordinate axis. So think of this as a new coordinate axis, right? Remember, all the coordinate axes are now sort of passing through the origin because we have sent the data. and they are sort of perpendicular to each other, right? This new direction is not. This can be any angle, you could say. At any angle, we will see that shortly. But define some direction randomly at first, and then project all data points onto this coordinate axis. Compute the sample standard deviation from that. And that's possible, right? Because now you have one set of values, one for each data point, right? After you project it onto this coordinate. You have one single vector of numbers. And then you can compute the standard deviation of that row. You can think of it as a row, right? In the table. The principal component solution is then the direction that maximizes this standard deviation. So it's actually about finding a direction in the p-dimensional space in such a way that when you project the points onto it, you get the maximum standard deviation. And then the further principal components after the first one, when you go hunting the second one, you do exactly the same, but with this restriction. It must be orthogonal, which is perpendicular to the previous component. So the second component must be perpendicular to the first one, but of all the directions who are that, you find the one again with the maximum standard deviation. And then when you go for the third component, you do with the same restriction again, right? Must be orthogonal to the first two. And of all the directions who are that, we can again select the one with the maximum standard deviation. So this is the sort of the procedure you do over and over again. And the principal components are then always ordered, such that the first principal component has the largest variation. The second one has the second largest variation, and so on. Of course, it could be that the second one is as big as the first one, right? It doesn't have to be smaller, but it has to be smaller than or equal to, right? It cannot be larger. So it's always a drop, or at least a constant, or it's the same value, right? Or smaller when you go to principal component 3, 4, 5, and so on. We will see that when we make the scree plot later. Okay, let's go to R again and demonstrate this. Let us have a look at a graphical view of how we locate the first principal component. And first of all, I have to say now, this script that I'm looking at here now, you can download yourself. I have a link on this lecture document here. Here you find the links. Just right click on this and download to your own computer. What you need is this script that I'm seeing here, which is called script_PCA. And then you also need this here because it contains some extra code that is needed by this script. And you have to put them both into the same folder, right, where you're running R now. So put it into your STAT340 folder. I have done that at least here. So let's run this code, and I first load our R package because I need some data, and then I source this extra file here with some, you see there are two functions inside it that we need. And then I set this random generator seed to 25 again. That's just to, because down here I sampled some random data from this body data set. So we have seen that body data set before. Let's load it. And instead of looking at the whole data set, we now look at, first of all, only 2 columns. And this is a little bit strange in the sense that PCA is something we do when we have many columns. But in order to make it understandable here now, we should look at only 2 columns, because then we can actually plot everything from the beginning. Also, I don't need all the rows. There are more than 400 data points in this data set, so I only need like 25. So that's where I need this random sampling here now. So I put this into a matrix X here that contains this data point now. So I put some row names on it, and let's have a look at the first part of it here. right? So instead of a table, it's a matrix, but that is just some technicalities down here. We could have easily had a table here. And you can see it looks similar, right? It's a first column with weights and the second column with circumferences. Each here is another person, right? So case 1, case 2, and so on. I just call them case 1, case 2, etc. now because I don't have any other information about these persons. Okay, that's our data set. First of all, let's just plot the data as points in now a p-dimensional space, right? And since p now is only 2, we can actually plot them like this in a 2-dimensional space, right? So this is not anything strange at all. And we can now sort of have a look at which data points do we see. This is case 17. And if you sort of project it into the two different coordinates here, right? Two different axes, weight and circumference, you can see case number 17 has a weight and it has a circumference. This one, for instance, is case number 2 with this weight and this circumference. And this one over here, case 16, this weight, this circumference. And we can actually go and look into the data. Let's see this case 2. If we scroll back up here, we saw case 2 here. Yes, it has weight 76 point something. Yeah, that looks like here, right? And it has circumference 73 something. So then we need to project in here. Yeah, 73, a little bit more. Yeah, that looks reasonable, right? This is case 2. So this is how points are located in this variable space, we say. Let's do the centering. So here I have some code to do the centering. And this is how it looks like now after centering. And notice that now the origin is in the center of the data swarm. Because along this axis we now have centered weight, which goes from minus something to plus something with 0 in the middle. And along this axis we have centered circumference now with 0 in the middle. So the origin here is in the center of the data swarm. And again, we can actually go and see if this here is still case 17, but notice now how the coordinates have changed, right? Because this one now have different values on the centered weight axis here and on the centered circumference here. This is case number 2, like we saw previously in case 16. And if we look at the previous plot here, notice how the points have not changed anything in how they are located relative to each other. The only thing that changes here is where the origin is. So as you can see, the distance between the points are exactly the same. So centering of the data does not change the relation between points at all. Nothing. But it changes the coordinate values, of course. So when you project into the new coordinate axis now, the centered coordinate axis, the values in the data table are different, but when it comes to how position between the points is not different at all. Let's now compute the standard deviation along each axis. How much does data vary in each direction here? And that's what I do here now. And then these thick purple bars here indicate one standard deviation in each direction from the origin. So this reflects the standard deviation along the centered weight axis, and this is the standard deviation, or two standard deviation, that since it's one in each direction, right? For the centered circumference axis. And we can see that, at least if the axes are scaled, that's a little bit tricky when you plot things in R, because you can change the aspect ratio of the plotting window, right? So you have to make sure that the units here and the units here are approximately the same in order to see a correct picture here now. So this is how far 10 units is on this axis, and this is how far 10 units is on this axis, right? Beware of this. You can be sort of deceived by a wrong aspect ratio here. But let's now go hunting for the first principal component. And what should we look for? We should look for directions in this space where we find the maximum variation. And then let's start out like this again. And now I go hunting for principal component directions. And let me just start out by choosing as my first sort of candidate for first principal component. I choose this axis here, which is actually the centered weight axis. Can you see it turned into yellow now? This is my first sort of candidate for the first principal component, the centered weight axis. And notice what happened here. When I choose this axis as my candidate for first principal component, I project all the data points into this axis, right? Projections into this axis to get values on this axis, and then I compute the standard deviation based on these values. So this is exactly the same as we saw before because it's the same axis, right? What if I click here? Then I choose a different direction, right? But it's also going through the origin, of course. And now we project onto this direction. And here is the standard deviation we got now, 10.93 something. If I click here and tilt this into another direction, we do exactly the same again, project into that axis and compute standard deviation. And we can see that standard deviation is smaller. And we can also see it visually here. It shrinks. So this is not good, right? This is bad because we wanted the largest possible variation. This gets smaller now. Now it's down to only 6 something. So we need to go looking in a different direction, right? And down here we find, look at the values. Now they are big, 17. And here it's like 18.5. But if we tilt even more here, it starts to shrink again, right? So now it's down to 16 and 13, right? Now we have to go back here. So inside here somewhere, we find the maximum variation. So let's say this is our guess of the first component. And actually, when it comes to computing the principal components, it's not done like this. There is a mathematical machinery behind this, but this visualizes what we are sort of seeking, right? We seek the direction in this coordinate system where we can find the maximum spread of the data. That's a good candidate for signal, right? Because we remember the PCA sort of criterion or idea, go looking for maximum variation. That's probably where you have some signal. This is not random, right? The big spread here is not random. The small spread in this direction is perhaps random, but not the big one here. This must be due to something more. So this is how we sort of look for the, or this is the criterion for finding the first principal component. And notice that the points are not, they are located at the same place all the time. It's only the axis that changes. We rotate the axis compared to the original 2 axes. So this is sort of a third alternative axis now. Yeah, if you click down in the right corner here, you stop this selection of directions if you want to run this yourself. So let's actually compute the principal components then and plot them. Because this we don't sort of search for it like this. There's a mathematical machinery, and this is exactly how it looks like now. And this is the first principal component, quite close to what we guessed, right? This one. And then the second principal component must be perpendicular to the first. So since we only have 2 dimensions, the second one must be here, right? It's the only way to get perpendicular to this one. But if you have many directions, p dimensional space, then there are sort of p minus 1 possible directions that are perpendicular to the first one. And you have to search among them in that sort of space then. It's slightly lower dimensional, and look for the maximum spread again. So the PCA plot that we usually see, or the score plot as we will call it, that will now look like this. And notice what happened here. We now replace the original axis with this principal component axis. So what we are actually seeing here now is a rotated image of the same data. So if you go back into here and you tilt your head to the left, you can see the data swarm is located now inside this yellow coordinate system, right? And what we did when we jumped here was that we sort of made this our sort of basic coordinate system instead of the original one. And then points are located like this. And the reason it looks slightly different is because notice here that the variation along the second principal component here is very small. So the data swarm looks sort of like a sausage, like here. But when I tilt it over here, it's like, so I should actually drag this aspect ratio down. Now you can see the same shape of the swarm. You see that? If you go back to the previous, then you have to go back here and look at the swarm here compared to if you look at the swarm here. And now we can again locate these points of ours. Where are they? Here you have case 17, here you have case 2, and here you have case 16. So they are again located exactly relative to each other as they were originally, but now represented in a new coordinate system. And that's actually the whole idea of principal component analysis. Find a new rotated coordinate system in which we can look at the data. So we have seen the idea for finding the principal components. So when we have found them, what do we do? And this is actually the crucial point. Dimension reduction. Remember this model here, right? The full variation is signal plus noise. Full data set, the signal plus noise here. And we also assume that signal is found in sort of fewer dimensions than the total data. How much fewer, we don't know, but this is the dimension reduction now. So instead of sort of choosing some randomly chosen variables from our original data, we now say that, okay, the first Q principal components contain the signal. And why is this? Yes, this is of course because here we have the big variations, right? In the first principal components, because they are ordered, the principal component columns here you could think of are ordered such that the biggest variation is first. So the first principal components contain the signal and the remaining ones are noise, and we are not interested in that, right? So the idea is now to just sort of replace, you could say, the original data by the first few principal components. And how many? Well, Q. We don't really know. So replacing the original columns with this rotated data. Because think of the original columns as axes, right? And these new columns are also axes, but they are sort of rotated in comparison to the original ones, in such a way that we get maximum variation along these directions here. If Q is as small as 2, we can now plot this in 2 dimensions, right? And that is also what we very typically do following a principal component analysis, regardless actually of how much signal we have in the first 2 dimensions, we plot them. But you should notice the signal may require more than 2 dimensions, right? It's a little bit naive perhaps to think that only 2 dimensions, especially if you start out with a lot of columns here, right? Then it's naive to think that it can be actually compressed into only 2 columns. But at least the 2 first columns are the ones who have the majority of the variation. So it always sort of makes sense to plot along the 2 first dimensions. But remember, it's an approximation, right? Because to only look at 2 components is often too little. It's sometimes sufficient. It's sometimes even 1 component is enough. But please remember this. And I should also say it's not forbidden to plot the other, component 3 and 4 and so. You may very well do that, but it's difficult to plot more than 3 dimensions, right? But you can plot component 1 against 2, and then component 1 against 3, 2 against 4, and so on. So that's legal. This is exploratory, right? We explore our data. But the point is, in the first principal component directions, we find the majority of the variation, and this is most likely the signal in our data. This is worth studying. What is the output then? Well, the first thing we typically look at is how much of the variation is captured along each of these principal component directions. And that is also often plotted, and that's what we call a scree plot. And that's the variance or the standard deviation along the first principal component, or actually along all of them in principle, but we're only interested in the first ones. And from this we should sort of try to make up our mind, can we see where the signal ends and the noise starts? And that's where we choose our cue, right? Which number of, how many principal components are needed, right? To capture all the signal and without starting to capture more noise. So here is a dream situation of a scree plot. And notice now what we see here. Along the x-axis we have the principal components in their order. So this is the first principal component, second, third, and so on. And here on the y-axis we have the variance. This is the spread, right? How wide the data swarm is when you project onto this principal component or this one or this one. And here we can very clearly see that the data swarm is very wide in the first 3 dimensions, and then we have a sudden drop here, and it's flat. And this fits exactly the sort of the principal component model that we sketched on the previous slide, right? We have signal here plus some noise here as well, of course, but then after 3 components there is no signal anymore, and this is the noise, right? Only noise here now. All the variations are small along these directions. So in this case we would set Q equals to 3, right? 1, 2, 3. 3 principal components capture the signal. Well, this is another situation. Sometimes the scree plot may look like this, and then it's actually no signal at all. Because here you could argue, okay, but isn't all the bars big? Well, no, all the bars are of equal size. Actually, the actual size over here is not important, right? It's the relative size. So when it looks like this, either you have signal in all dimensions, which is hardly the case, or you have signal in no dimensions, which is more likely. This is only noise, right? And this doesn't happen very often either, unless you have some really rotten data, I would say. So what is the typical situation is something like this. Something like this. This is more how it often looks like, I would say. Where you have some very big bars here at the first principal components capture something, The last components capture almost nothing, and then there is some place in between here where we should draw the line. And it's not obvious. That's my point. In the very first plot, it was this very obvious drop. It's often not very obvious, this drop. It drops gradually like this. So it gradually sort of fades from more signal, less signal, less signal, and gradually fades out like this. And then we have to just make up our mind and say, okay, perhaps here or here, right? But you can see that in such a situation, if you plot the first two, if you plot along the first two principal components, we will still capture quite a lot of the variation, because these two together, if you add them up, they are much bigger. They are at least 50% of the total if you add up all the columns, right? So when we talk about explained variance, we usually add up all the column heights to get the sort of the sum of all of them, and then we look how big are these first one compared to the total as a percentage, right? That's really easy to grasp. Okay, PCA output from the function that we use in R, we get what we call a loading matrix, and this is actually the directions of the principal components as rotations of the original centered variables. So this is the loading matrix tells us in a way where the principal components are, in which directions they are, as a combination of the original variables, centered variable. There is one column for each principal component and one row for each of the original variables. We will see it a little bit more in shortly. The other one, and this is perhaps more often focused on, the score matrix. And this is the original centered data cases in the new coordinate system. So this is sort of the data matrix, you could say, the new data matrix. If you think back on the previous slide, this black small matrix, this is the score matrix, and it has also one column for each principal component, of which we choose then a subset, right? And one row for each data case. So this matrix looks sort of like the original data in terms of rows and columns. It's just that the columns have been replaced by the principal component. So let's have a look at how this relates to each other. So here we have the a super small data set then with two variables and two data cases. And we have centered data, as you can see, because the average in both columns are 0. And then you have the loadings here, right? The loadings for PC1 and PC2. And notice there is one row here for each of the variables over here in the original data set. So a loading matrix will always have, when you have P variables here, there will be P rows in this one, and one column for each principal component. So these are the loadings in this case, and these numbers were then computed by the principal component analysis. And here we have then the score matrix. And notice again, this looks much like the first one again, right? With data case 1, data case 2. But instead of the original variables, we have the principal components now. And how are these sort of related? How are these values related? Well, you can see here, this green minus 1.8 here comes from the fact that we have these values here in the first row multiplied with, or in the product with, the first column in this here. So you take 1.6 times 0. So you actually sort of rotate this one, this vector here, with this here. and then you get this number here. And the same for the second one here. Then you take this row here and rotate it with the same principal component, right? So these are the values you have, right, when you project onto the original V1, V2 axis. But now we sort of rotate the axis using this one, and then we get new scores here, 1.8 along this PC1 axis. And the same, of course, for the PC2 axis. But the only difference is that again we use the original data, but now we rotate with this column instead, and end up at this values here. Yeah, this is a detail, but it's sort of important. It tells us how these three matrices are related, right? The original data one, the loading, and the scores. And you can see we compute the scores using the loadings on the original data, rotating the coordinate system actually. So plotting with Q equals 2. The loading plot. The loading plot is plotting the original variables as points in this PC1, PC2 coordinate system. So we plot the variables, right? This tells us a little bit about the original variables, how they are sort of located now, once we have rotated the axis. Where are the original axes sort of compared to this new axis? So we can imagine lines from the origin to each point here now, as a sort of as if it was an axis, right? Small angles indicate similar variables. Yeah. That's a point we will come back to. So if two variables are located with a small angle between them, they are correlated or similar. The score plot. The score plot is much more common to use or to see. And this is what people often call a PCA plot. And here we plot the original data cases, but now in the new coordinate system. And this is where we typically plot in PC1, PC2, right? And that's also the case up here though, because 2 dimensions is easy to understand, right? But remember this, 2 dimensions may not be enough to capture the whole signal, so please remember that whatever you see here is not the full story. It's not the full story. There is something that you don't see in a PCA score plot, or also in a loading plot. So you should always check that scree plot first to verify that the first 2 components capture a lot of the variation. Otherwise it's not as informative. It's still some information, right? But it's less than if the first 2 coordinates are containing a lot of signal. Yeah, and of course you can plot the other coordinate axis as well and inspect them. Score plots and actually OR plots are explorative here. So don't be afraid to sort of do something wrong here, because you can't really do anything wrong because this is explorative, right? Just plot. If you don't see anything, okay. But if you find something interesting, it may be worth pursuing, right? So what should you look for? Well, you should look for grouping of data cases or gradients, I would say. Grouping or gradients. And we will see that when we do some practical plotting. That's what you should look for. It can also reveal outliers very nicely. So if one data point is sort of way far out there compared to the rest, this may be revealed in these plots. So that's information, right? It means that you should go back to your original data set and look for something strange there. So the whole point is to generate some ideas and hypotheses it's not conclusive. You cannot draw conclusions based on PCA plots, I would say. They indicate things, and but there's no sort of formal testing of anything, or yeah. Okay. You can also make what we call a biplot, but that's just combining the score and the loading plot into the same figure. So it's more a technicality. Personally, I don't like them really because they tend to be too crowded, right? I would like to have them separated as two. But that's your choice, really. I mention it. It's sometimes used. People prefer differently. So let's go back and have a look at these plots in R. Let us run some PCA on some data. And here we look at what we call the beer taste data. So let me just copy this first part of the code here, where we load the tidyverse and the bias package in order to get hold of this data set. And then we take a look at it. I made myself a script here now that I call script week 2 in my STAT340 folder. So let's just run this. Yeah, source like this, loading the packages, and there we have the data set loaded. Yeah, I can actually run this again just to have it appearing here in the window. So we can see there's a lots of variables here. All of them, no, not all of them. Most of them are numerical, right? And there are some factor variables at the end. These are some beer tasting data. So actually, if we open the data frame here, each row here is a person I remember, and then they are giving like liking scores to different ales and so on. And we also have the age and the gender, male or female. And age is not numerical, it's only categories, old or young. And some position here. And I think that in this script here now, the first thing we do here is some data wrangling. And actually I will just do that now without commenting much more. I just copy this code because I find that this dataset is a little bit, what should I say? It doesn't tell us too much, right? This single letter codes and stuff. If you look up the help page for this beer taste data, it will explain them. But I mean, instead of O, we could type old, right? And M male instead, and male and female, right? S student or work. Why don't they type this? I mean, this is stupid to have this single letter coding when it doesn't really, it only makes us confused, right? So I would spend this much time to fix this. The beer taste data, which is now sort of the alternative, where we have proper texts, right? And also in this, these column names here are also the same. Not very good. So I would replace them with some proper column names here. If you read the help text, as I said, you will find that this is what it should have been, right? So why don't we do it? It's so much easier. And then we put the column names in here. So now we can look at the beer taste. And now we can see proper text. Ale 1, Ale 2, Lager 1. These are beer types, right? So now it's so much easier to understand what it's all about. But this was not important. This was just frustration over unannotated datasets. Here is the important part. We want to do some PCA now. And notice the data here. We have, I should click away. We have these factor columns. And when you do principal component analysis, you can only do that on numerical data. Only on numerical data. Because remember what we did, we projected the points, right, onto this axis and so on. And that means you need to have some axis, right? We don't really have that here. It is categorical data. these are not numerical axes. This is not a coordinate along an axis, right? These are text. So we cannot use this numerical data. Sorry, the categorical data. Only the numerical data. PCA using numerical data only. And that's what we do here. Let me just copy the code first. Like this. So notice we say use this table, but only from column 4 to 12, not the 3 first column, right? Because they are not numerical. But we can do principal component analysis on the other columns here. And the function to do principal components in R, at least one of them, is this one, prcomp. And the only input required is the data table or matrix. Both can work here. But remember, it must be only numerical data. No factors or text. And then we get some object back out from this function that we store here. And we can have a look at it. So let's run this code here. Zap. It doesn't take a long time. If you have a very big data table, it can take some time, some seconds. It's not like forever, right? But sometimes it can sort of hang a little bit, right? Half a minute or so. If your data table is super big, especially if you have super many columns. Let's look at the summary of such an object. What is a summary of such an object mean? And this is quite useful, actually. Look at the output here. Because it now lists actually the standard deviation or variance for the different principal components. So here we can see in the first principal component, the standard deviation is this big. And here is in the row below, proportion of variance. So if you sum, first of all, convert from standard deviation to variance. That's just by squaring, right? And if you now sum all the variances here, and it continues here, you can see PC 6, 7, 8, 9, because there are 9 columns here, right? So if you sum all the variances here, you get the total variance. So this one here means that in the first principal component, you have 31% of the total variance in this direction only. In the second one, you have like 17%, and then 15%, and 10%. We can now sort of visualize how this scree plot will look like. This is the same information, right? And in the third row, it's just a cumulative. So it starts out with the same value as here, but then you have, if you add together these two first, you will have this much, right? So we can see that almost 50% of the variance is captured by the 2 first component. Not too bad. It means that there is quite some signal here in the beginning, but it's not more than half of the variation then, right? And we can see towards the end here now, there are very little variance, right? The last few principal components, this is noise, right? So there is no signal here, but it might be that only the 2 first is a little bit too, we should actually at least go to component 3 or perhaps even 4 and 5. That's somewhere there. But that's the summary. Let's look at the scree plot. And I mean, a scree plot can be made in several ways. I have made some ggplot code here because I like to have it in that I like to have plotting in that framework, you could say. Yeah, I don't really need to load the tidyverse again because I already have, but it doesn't matter. And then I compute myself what I call a scree table here. And we can actually compute it before we have a look at it. So what is this? This is now a table where I have one column called just PC. If we look at it, if we pop it up like this, one column here which is just numbering the PCs, 1, 2, 3, 4, right? That's the first thing here. And then the variance fraction, that's actually the same thing as here, right? But this I now compute from inside that PC object. There is a vector called SDEV, and that's the standard deviation. That's this one. They are actually found inside this object. If we look up the object here, you will see inside there it is, SDEV. It's just this vector of values, 2.66, 1.97, yeah, it's the same. So I take this one, square it to get the variance, of course, and then I divide by the sum of this. I do exactly the same thing down here, you can see, but then I sum up all the squared values. So this will now become the fraction or the proportion, right? The same as we have over here. And then I plot using these two, the PC along the x-axis and then on the y-axis. So let's do the plotting and see how it looks like. This is how it looks like then. The first component, a little bit more than 30%, and we saw up here, yeah, 31%. The second component is like 17, right? We saw it up there, and then drops only to 15 here. So actually, we could argue and say, okay, after three components, it's not that much left, right? So we could choose Q equals to 3 here, ideally. But when it comes to plotting, we choose always Q equal 2, you could say, for practical reasons, because we need to have a two-dimensional plot. Let me just show you this. This is just an alternative code. If you don't want to use my sort of template for doing it the tidyverse way, there is a package called Facto Extra that contains some interesting stuff. Among those, a lot of functions for plotting PCA results. So there is actually a scree plot here. Whoops, I should of course load the package and then make the scree plot and show it. And you can see this, it's the same figure actually, but they add some fancy stuff here. So that's up to you how you choose to make the scree plot, but it contains the same information, right? The score plot then. Well, let's make a score plot and let's copy this code here first. So how do I make the score plot? Again, in the ggplot version, again I make myself a table. And this is just a copy now from, you can see that this PCA object has an object inside called X, and this is actually the score matrix. This is a score matrix. So if you look at here it is. So this is actually a matrix with 34 rows and 9 columns. So I just convert it to a data frame because it's a matrix inside there. So I wanted to have it as a table. And then again, I compute this variance fraction. That's the same as we did up here. Because I only need that for putting some labels on the axis. That's the only reason for this one. You don't really need it for the PC, for the score plot itself, but it's customary to put this information on the label, in the labels on the axis, as we will see. So I just plot now from this score table. If I run this, let's have a look at it. If I run this line of code and we look at the score table, you can see that this is now sort of a data table, just like the original one, the beer taste table, without the factors. And remember, everything has been centered and so on, so that's why it may look a little bit messy here. The nice integers we had originally is sort of gone because of the centering. And instead of the original variables, we have the principal components. But the rows are the same, sort of. So the persons 1, 2, 3, 4 in the rows here are exactly the same as here. And yeah, so when we, and then we compute this variance, and then I make the plot, and it looks like this. One dot for each person, right? It's a scatter plot. And now the values we put, we use the principal component 1 and 2, right? So this is now principal component 1, and this is principal component 2. So this is how the points are located in this new coordinate system. And you can see the only reason I needed this variance fraction is because I add it as a text to the axis. So it says PC1 and then parentheses 0.31. So it means that 31% of the variance is along this direction, right? And then I put 0.17 here. So the 17% of the variance is in this direction. And now this is a point that you should remember. When you see this plot here, it says that this is 31%. Or actually the spread along this axis is actually twice as big as this one. Can you see that? Approximately then, right? Twice as big here. But the plot, the aspect ratio of the plot doesn't really tell us. So actually we should now lower the y-axis like this, right? So that it's sort of, the plot is sort of twice as wide in this direction as it is in this direction. Otherwise, it's sort of a visual, we are deceived by the aspect ratio of the plot. So the main variation is here and much smaller in this direction, right? We can see it from the numbers. So this is something to remember when you show score plots or PCA plots to people. Try to make the aspect ratio following this values here. Otherwise, I mean, we could even make it like this, right? And it looks like that there's a big difference in this direction and small differences here. But this is a lie, right? This is lying about the data. The truth is actually this, right? The big variation is in this direction and not so much here. Yeah. Okay. Let's go looking for, okay, I can also show this alternative score plot in this other, using this factor extra way of plotting it. So they also have a way of score plotting, and that looks quite different, you can see, but it's the same information, except they have sort of put this numbering on each dot then. Well, we will come back to that. I don't really like that, but we will come back to that and see why. Because, and that's actually what we are doing now. Whenever we see a score plot like this, what are we actually looking for? And I would say what you always look for in a score plot, or the first thing you look for, is if there a grouping of the data cases, or is there some gradient? And what do I mean by a grouping? You can understand, right? If some points are sort of forming a group somewhere, and some other points are forming a group some other place in the plot, then it's a grouping, right? But what do I mean by a gradient? Well, a gradient means that you have a gradual transition of something. And in order to see if you have a gradient, you need to add some further information to the plot. And that's typically what we do with coloring the dots, right? And that's what we will do here now. So let's color the dots by, for instance, this gender information, male or female. So let me copy this code because, and this is why this GD plotting is so nice here. Adding color. So notice now, again, I make this score table, but then I pipe it in, or I pipe it into this bind calls, which actually just binds together two tables. So I have one table here with 34 rows, and we have the original data table here, also with 34 rows, and the rows are in exact same order. So we can just glue them together into one big table. So let me do that. So after this has been, let's inspect the score table now. It looks as before, but if you go out to the right, here you can see now we have the original data also included in this. So we have both the principal components and the original data in the same table. That's nice, right? Because now we have this information here, these factors, and those we can use for coloring. For instance, gender then, right? And the rest of the plot is now the same, except that I use now this column gender for coloring. So apart from that, the score plot is as before. I actually made the size of the dots a little bit bigger as well. And now you can see the same, this is the same plot as we had 2 pictures ago. Same plot, but now I have made the dots a little bit bigger, and I also make some colors. And again, we should sort of make the aspect ratio a little bit more correct like this. And now we can see that the females tend to be on the right hand side here, right? And the males tend to be on the left hand side. And this is exactly what I mean with a gradient. You can see there is sort of a transition from male towards female in this plot. So if you have a high score on the PC1 axis, that's more like the females. If you have a low or negative, large negative score, it's more like the males. Of course, it's not 100%. There are some, but this is a sort of a picture, right? A general trend we can see when we inspect this plot. And this is typical something you do when you make these score plots. You add some additional information that you have about these data points, either as coloring or as texts or whatever, to each dot, so that you can actually see if there is a sort of a gradient, if there is a systematic variation somewhere. Or if everything is just scattered wildly and randomly around, okay, that's also some information. There is no sort of gender effect. If that was the case, we would say, okay, male and female, they like beer in more or less the same. It's random, right? But it's not, it looks like here it's not. So this is beer liking. It seems like the females and the males tend to like slightly different types of beer then, perhaps. Okay, let's have a look at the loading plot. And the loading plot is, again, the ggplot way of doing it. I do it more or less the same way as I did with the score plot. I take out from this PCA object an object called rotation, and this is the loading matrix. I don't know why they have chosen this rather strange name. Why did they call the score matrix X and the loading matrix root? Yeah, this one I can understand, rotation, but this is a strange name for a score matrix. But anyway. And I put it into a table where I put some row names. No, sorry, the row names are converted into a variable inside the table. That's what I do with this code here, because this matrix has row names, and that's actually the names of the variables. So now I want to put that inside the table. So if I run this one and we look at it, loading table, you can see the first column here now is actually the names of the variables. And then we have the loadings out here, one for each principal component. And then, and this is a trick, I make another table with zeros in it, and that's just for the plotting later. So yeah, you can look into this in detail yourself. But this is only for making the plot nice, I will show you. And then we plot again with along the first 2 principal components. I plot both as points, and I add texts, which is sort of the name of the variable, to each point, right? And then I also add some line here, and that's why this origin table comes into play. Let's see how it looks like first. here. So this geom point, that's the small black points, right? The geom text adds the text on the same locations, so that's the name of the variables, right? And that's nice to have in a loading plot. This you could also do on the score plot, right? If each data case has a sort of a text that you want to put on the dots. We could have put on male and female, right? Instead of color, but color looks better. And then finally these lines, and that's these maroon lines going from the origin. So here we have the origin, right? Here is 0 along PC1, 0 along PC2. So that's sort of the center of gravity, right? And these maroon lines indicate now the angle for each variable out from this origin. And the point is now that if two variables have a very, for instance, these two here, they have a very small angle between them. They point almost in the same direction, indicating these are very correlated variables. But they don't have a very big score. They have not a very big score in PC1 direction. Slightly negative, but not super big. Almost nothing in PC2 direction. Can you see that? Because they are very close to 0 here. So the really important variables for PC1 direction is this AL1. Right? That's a very big score here. Positive. And there are some others here. And now we would interpret and say, okay, the people who like this one, they sort of tend to dislike these ones on the other side, right? And also perhaps here, if they, but especially the first principal component, which is the most important one, they are sort of opposite, right? These ALs are opposite of each other. So the people who like one, they don't like the others, and vice versa. So variables lying almost on the same line are positively correlated. If they are lying opposite directions, they are negatively correlated. And if they are orthogonal or perpendicular, they are uncorrelated, right? So for instance, this AL2 and AL3 is almost a 90 degrees angle here, right, between them. So they are uncorrelated, indicating that whether people like AL2 or not has no information about if they also like AL3. That's independent. So yeah, strong lager 2 has little impact on principal component 2, but not much on PC1 either. And yeah, it's a little variation between the beer tastes. Strong lager 2, where is it? Yeah, it's this one. Yeah, it has a sort of a short distance from the 0, right? From the origin. It means it has a little impact. And the AL1 has a huge positive loading on PC1. That's this one, right? And now we should remember that when we looked at the score plot, let's go back here. When we looked at the score plot, we also saw that, okay, a large score along PC1, that's more typical for the females, right? And now we see this plot here, okay, large score for PC1, that's also typical for AL1. So that should sort of indicate to us that females tend to like AL1 versus males who don't like AL1 very much, because they are on the opposite side, right, in the PC1 direction. So that's sort of information you can directly see from a plot like this. And if you want to go back to the original data and have a look at this, we can actually do that by making a box plot. Right? We take the original beer taste data now, we make a box plot where we use the liking of AL1 as the y-axis, and then we use gender as the x-axis. And then we see it directly here. Can you see that? For the females, AL1 liking is pretty high. The females like AL1, while the males now not so much. And that is exactly the information we sort of saw now in the loading combined with the score plot when we had this gradient information. Okay, we can also make this biplot where you have both score and loading in the same plot actually. And that's sometimes preferred. I'm not a big fan of it, but then you can see this AL1 out here, right? Together with, but now you don't see the, we don't have the coloring information anymore, right? About male and female. Well, I guess you can add colors to this one as well, but it's not as straightforward as it was when you do the GG plotting yourself. So that's why I prefer the sort of basic GG plot. But this is a nice figure as well. So do it, use it if you like. Okay, some mathematics, and this is for those of you who are familiar with the linear algebra. You may have gotten the impression that we go hunting for the principal components by some sort of random search. Well, that's not really the case. So let me set some things straight here, how we actually do it. First of all, let's say we have the data, the numerical data in a matrix X here, right, with n rows and p columns. Then we can always compute what we call the covariance matrix for this data matrix. So, and this covariance matrix indicates how the different variables covariate. So if the original data matrix has p columns, this becomes p times p rows and p column. And actually we computed a correlation matrix last week, in the first week, and that's almost the same thing. So it tells us how different variables correlate or covariate with each other actually then. And then we compute the eigenvalue decomposition of this covariance matrix. And this you can do, this is our code in the parentheses here. So the eigenvalue decomposition, and I'm not going to explain what it is, so if you don't know, just skip this. The eigenvectors are the principal component loadings. So that's really the eigenvectors of this covariance matrix. The eigenvalues are the explained variances here. And the score matrix, Z, if we call it Z, that will then be n times q if we have sort of only considering the q first principal components. This is then computed from X and the loadings, right? And we saw this actually earlier as well, but let's see it again here. Here we have the original data matrix, X, like this. Then we compute the loading matrix, actually the eigenvectors, right? Like this. And we have the, the eigenvalues here. Or actually normalized. Sorry, this is a normalization step. That's what I was. So notice that we say that okay, the values of this one are all they all scale to 1, right? Sorry, sum of square is 1, so it's sort of a restriction to this loadings. And that makes it a rotation, otherwise it would also be scaling the original axis. And then you find the scores like this. You take the original data and you just rotate by the loading matrix. So this is an inner product, right? Or if you write it in a component form like this, then the score for row I, column J, you find like this. And we actually saw it in that numerical example a couple of slides ago with where I colored this differently, right? Red, green, and blue. So then you get the score matrix here. So the score matrix is sort of a product of the original data and the loadings. This is sort of worth remembering for later, because we will come back to this actually in a couple of weeks. Yeah, so this is then the truncated or the compressed score space, right? If we don't use all the loadings, we use only up to Q loadings, right? And then we get up to Q columns in this one as well. Data standardization. That's something we need to mention when it comes to PCA, because PCA is sensitive to the scale of the variables. And that follows actually from maximizing variance. Let me illustrate this. In the body data that we saw in that previous video, we had a variable called age, where the age was measured in years. What if we measured age in days instead of years? Well, that means you just multiply all values in that column with 365. And the standard deviation grows accordingly. So if the standard deviation was originally S, it becomes now 365 times as big. And of course, when you go hunting for the biggest standard deviation, this becomes really important now, because this was perhaps not such a big standard deviation originally, but now it may be super big compared to the other standard deviations, right? So it means that scaling affects where you choose to put your principal component directions. And we should ask ourselves, is it reasonable that the principal component should be affected by this scale? Well, I think that it depends. It depends. This is not a clear yes or no to this question here. We may standardize the data prior to PCA by doing like this, and we have seen that before, right? How we standardize data for each column, compute the standard deviation, and divide all values by this standard deviation. That's the standardization. And this is the way we can sort of this is what we can do to avoid the scale having an effect, if that's what we want. If we don't want the scaling to have an effect, then we should do standardization. And in mathematical terms, with respect to the previous slide, instead of running the eigendecomposition on the covariance matrix, you now use the correlation matrix instead. That's exactly the corresponding way of, I mean, doing this and then do the ordinary procedure is the same as doing the eigendecomposition on the correlation matrix directly instead of the covariance. So data scaling and interpretation. When should we standardize the data? Well, typically if variables are in different units. So actually that body data example, I think I would argue that here it makes sense to do standardization, because there was one variable called age and another one was weight, wasn't it? I mean, how can you compare age in years to weights in kilograms or whatever? I mean, it doesn't make sense. So we should standardize, I think, in this case, because we have measured in very different units in uncomparable, right? Really. Also, if you want sort of relative rather than absolute variation, then you should also standardize. But on the other hand, if your variables are like sort of counts, for instance, or in this beer taste example, where all the values were on the same scale, right? People were asked to give sort of grades to the different ales they were tasting, and the scale is the same for everyone, right? Then it makes sense to not standardize, because then you may lose some important information, right? If you do, because then you have comparable variables. They are of the same scale. If you are in doubt, try both, because this is explorative, right? There is no sort of rules here. And if the plots differ a lot between using standardization and not, you should try to understand why this is the difference. And we will see some examples of this in the exercises. So what are the new axes of the principal components actually measuring? They are all combinations of the original variables, right? So the loading plot tells us a little bit on how much each of the original variables affect the new axis, the new principal components, right? Those who have a big loading, positive or negative, in either PC1 or PC2 or PC3 direction, are the important ones. Those who are close to the origin, close to zero, are not important. You should also be aware that the signs, both in the score and the loading plot, I mean the signs of the principal components are almost random. So if you, and that's something you can experience sometime. You make a PCA plot and a principal component analysis, and you plot your data, and then you make, let's say you remove from the data set a couple of rows, right? Perhaps there were outliers or something, or for some reason. You change your data set slightly, and then you run the PCA again, and you get almost the opposite picture. And that's not, don't be surprised by it, because the signs is not really important here. Whether it's positive or negative, what is important is how far away from zero you are. And that goes for both the score and the loading plot. So you can get almost sort of a mirror reflection plot sometimes, but it contains actually the same information. And patterns that you should look for is in the score plot. Look for groupings or gradients. That's the important information, I would say, in the score plot. Okay, let's do a small R session again where we see some standardization. Let's have a look at this data set called track records, and for illustrating this effect of standardization or not. So I have just in my script here, let's just load the data and look at this track records. Yeah, I should make this window bigger. You can see what it is. It's a matrix with some national records in the running, I think, for different nations here, quite a number of nations. And this is the records for running different distances, right? From 100 meters up to marathon, which is a very long. And I think all the values are sort of in the same unit here, isn't it? In minutes. Yeah, it looks like it's in minutes. I think it says here somewhere. Yeah, again, there are some small data wrangling that we can do here in order to make this a little bit prettier. First of all, we should, yeah, let me put in the code. I would use, instead of having row names, I will put the nation or the country names inside the table and delete the row names. A table shouldn't have row names, right? And also delete this X from this. I don't know why this was included in the first place. So let's run this and have a look at the track records again. Now we can see 100 meter, 200 meter, and so on. And the country name is inside here. That's better, right? Now it's a proper data table, I would say. That was not the important one though. Let's run a PCA on this numerical data. And now remember, the last column is not numerical now, so that's why I only look at column 1 up to 8, because the first 8 columns are the numerical ones. So we run PCA on this one, straightforward, and then we do all the plots that we did previously, and now I just copy everything here. right? The scree plot, the score plot, and the loading plot. So the scree plot first. That's this part, right? And look at this. What on earth is this? Here you really can see that signal is in one dimension only, right? It's one super big, almost 100% of the variance is explained by one single principal component, and all the other ones, they are so small you don't even see them here. This is noise, right? Rubbish. One principal component. And if we do the score plot based on this, and of course now it makes, actually now, remember now, 99.6% along this axis, almost nothing here. So now we should really turn aspect ratio down to almost like this, right? But okay, we don't see the text, and so let me make. But remember, the variation in the vertical direction here is almost, it's nothing really, right? Doesn't mean anything. It's only in this horizontal direction that we have some information. And here we can see these are different countries, right? So instead of making dots as we did in the first score plot, I only put text now, because that's, we couldn't use coloring here because all the names are different, right? So this is the score plot, and we can see, okay, Cook's Islands, these are some very small nations, aren't they? Papua New Guinea. These are some very small island countries. And in here you have sort of the big countries. And so it means that the big scores, in this case negative, are for these very small island nations, whatever that means. But that's something strange here. Let's look at this loading plot. And now we can see really what has happened here. Wow, what was this? We can see that the principal component 1 is completely dominated by one of the original variables. And that's the marathon. That's the marathon. And we can see that principal component 2, which is not really important though, but the small rest information, you could say, the tiny little rest information, is in 10,000 meter and 5,000 meter running. And notice that all the short distances are in here. So what happened here? Let's go back to the data table and have a look. If you are going to find the direction with the largest standard deviation here, this is of course reasonable, right? Because if you look at the 100-meter records, these numbers are almost the same for all nations. And that is because when you run 100 meters, it's a short distance, and it can't be a very big difference between how fast you run, right? So the records for all the nations, even if they are relatively different, they are on an absolute scale very similar. Well, when you come to the marathon, simply because these numbers are much bigger, there's also a much bigger difference between them. And that is exactly what we see here. When we use the data as they are, the principal component analysis is completely dominated by the variable having the biggest values. So this one, so actually principal component analysis tells us nothing more really than saying that, okay, marathon is the variable with by far the biggest variation in records. And that is not so surprising. It's like measuring the height of trees, right? It's the difference between big trees is always bigger than the difference between small trees. So in this situation, it makes sense to do the standardization simply because we are not interested in the absolute standard deviations, but rather the relative ones. So we should sort of look at how things are relative to how big the values are in each column. So let's try to run the analysis again, and this time with the standardization. And how do we do that? Well, here is how you do it. I commented it out. But now I can copy it and put it in here, and instead I comment out the previous one. So you can see it's almost the same command, but you say scale dot equals true. Then it will be a standardization as well, before, in addition to the centering, which is always there, and then the principal component is run. So let's run this one, and now we can make the plots again, all of them. And let's go back and look at the scree plot for it. Still there is quite a big domination by one component only, but now it's a little bit more on the other ones, right? It's not so completely dominated by one direction. And I should actually say that when you get a scree plot where one variable is or one principal component is completely dominating, you should be aware. This is sort of a warning, because it could be you have some outliers or some really strange data in there. So remember that. If we go and look at the score plots now, well, it doesn't change very much. We still have these small nations out here on the plus side this time, but as I said, the signs are almost random, right? So it means that when it comes to this track record, these nations are on the opposite side of these nations, right? USA has the largest negative score here. And I think that these are the nations with the very good runners. USA, Kenya, Great Britain, and so on, right? So these are probably the poor runners then, since they are on the opposite side. I don't know. And the last figure, yeah, here we have the loading plot now changed dramatically. But notice now, all of the records, all of the variables have a positive loading. All of them have a positive loading, which indicate along the first principal component, which indicate that they are very correlated, or at least quite correlated, right? Since they all go in the same direction. And that's not so surprising, because I think that if a nation has a good record in one of the distances, it tends to have a good record in the other distances as well, because it says something about how running as a sport is sort of has a status in that nation. Probably, I don't know, but I would guess so. But also notice that in the second direction here, we have still the distances from the shortest gradually to the longer and longer distances. So it's still an effect of distance, but that's now the second principal component. The first principal component is sort of the general goodness in running for each nation. So that was a dramatic actually impact of doing the standardization. And in this case, I think the standardized analysis was the more sort of informative one. Let me finish this rather long lecture with a few words about multidimensional scaling. And this is not really mentioned in the R book, but I thought it was worth adding it anyway. And what is this? It's also something called principal coordinate analysis, and you can hear by the name this is quite similar to PCA, so that's why I added it here. The data we have available are not always a data table with n data cases and p variables. It's instead a distance table, an n times n distance table, so a distance between the data cases, right? For instance, distance between cities on the map, right? Or it could be the similarity between different DNA sequences. And in these cases, there are no sort of, I mean, on a map you have a coordinate system, but in the DNA alphabet you have no coordinate system. So there are no sort of underlying variables, or at least they are very difficult to define. But the distances can more easily be defined. And also, I think if you think in terms of distances on a planet, on a sphere, you also have troubles with coordinates, right? Because it's a round surface. Anyway, sometimes we have data of this type here. And then we typically use principal coordinate analysis instead of PCA, even though it's very similar in, if you go to the mathematics of it, it's almost, this PCOA uses PCA actually. So the data input is a distance table. That's the big difference. It tries then to reconstruct variables. So this PCOA tries to construct variables as well in such a way that when you compute distances based on these variables, we get as close as possible to the original distances we have as input data. Right? So it tries to sort of reconstruct the map, you could say, and placing the cities correctly related to each other. Of course, it could be rotated and flipped around, but at least relative to each other, the distances should be correct, or as close as correct as possible. It's not given that it's possible to make it exactly like the original distances, but as close as possible. And then we typically plot using the first two variables again, just like with PCA. So that's no difference, right? That's no difference. This is also called classical multidimensional scaling, and there are some variants of this in use quite a lot. For instance, non-metric multidimensional scaling, but it's the same idea. So I don't dig more into that. Only the sort of the classical one here now. So when should you use PCA or when should you use the PCOA? Well, simple answer: if you have a data table with original variables, you should use PCA. I can't see no reason why you should go for this other one, because it's sort of, I mean, then you would have to take your original variable, compute some distances, and then try to reconstruct the original variable. That doesn't make sense. If you have the original variables, you use them, of course. But sometimes you have no coordinate system, only the distances, and then you use the principal coordinate analysis. Or actually the relation between the data cases are not properly described by the coordinate system. We will see some example of that, where we use, for instance, a distance metric which is not Euclidean. Then it makes sense also to do PCOA. Yeah, so in some cases when you have a coordinate system, you may still want to define similarity in a non-trivial way. That's what I'm talking about. And then this may be interesting. So, then you first make PCA from the data table, compute some distances, and make a principal component analysis on the distances, and compare this to the PCA. Do you get the same overall information? Well, most of the time I would say yes, unless this similarity is really different from the Euclidean or ordinary distance metric, as we will talk more about next week. So let's have a look at an R session here at the end to see how we can do this principal coordinate analysis instead of PCA. So let's have a look at how we do this principal coordinate analysis then. And here I just create a sort of artificial example where we have this beer tasting data again. And now instead of using the original variables, I compute a distance table. And this we will look more at next week when we look at clustering. Then we will talk much more about this distance metrics. So for now, let me just do it like this. There is a function in R called dist for computing distances between rows, you could say, in a table or a matrix. So notice now I only used the numerical data again, of course, from this beer tasting. I think I still have it here. Yes, we can click it open. The three first column were factored, so it's based on the rows here now. Yeah, let me click away some. And then I use a method called Manhattan, and the Manhattan distance is slightly different from what we usually call distances, but it's not that different. So I guess these results here now will not it will not look very different from what it did when we did the ordinary PCA. But anyway, let me just do this to show you the procedure. We will do more of this in the exercise. So here we now have a distance table, and this is now just, we can actually have a look at it here, beer dist, and this is a slightly strange format you might see in let me just click away this plots here now. In our distance matrix, it's actually a matrix, right? So in this case we had like what was it, 31 different data cases, so it should be a 31 times 31, but it's not represented as a matrix. And that's of course because it's symmetrical, so it's only the lower half of it, the lower triangle, right? Because always the distance from A to B is the same as from B to A. So the values in row I, comma j is always the same as in cell I, comma j is in same as in cell j, comma I. So these numbers are not printed here because they are exactly the same as here down here, right? 1 point in column 1, row 6, or in row 1, yeah, it's actually row 2. You don't even see the row 1 here because it's only the lower triangle. You can actually convert it into a straightforward matrix, but we don't need to do that. And here is the command for making the principal coordinate analysis. It's a simple CMD scale. It's called CMD scale. It takes as input the distance table, and then you also have to specify how many of the original variables do you try to reconstruct. And since we are only using it for plotting, we only want to have the first two variables, two dimension. By increasing this, you get sort of a more precise reconstruction of the distances, I suppose. But since we are only using it for plotting here, we don't need more than two. And then it will output simply a matrix with these values. So let's try to do that. Like this, and then we can have a look at this PCOA matrix. Where is it? Here. Yeah. And then you can see two columns, two variables, and these are now the coordinates for the different the beer tasters, right? In this reconstructed variable space. So this is sort of an alternative, you could say, to the principal components, but based now on distances instead of the original variables. I add some proper column names to them just to make it a little bit prettier, right? Instead of V1 and V2. But that's the whole procedure really. And now we can do a score plot just like we did before, but based on this information instead. So in principle, we now make a score plot where we take the original data, bind it to this matrix here, so we get all the information in one big table, because then we can plot the points and color by gender again, just like we did before. Let's try to do that. And here we get the results now from the principal coordinate analysis. And if you go back and look at the score plot we had from PCA, you will see it's not super different. We can still see this gradient across from male to female, right? But it's not 100% the same. And that is because we now use the Manhattan distances. If you had one thing you can actually do now is to replace the Manhattan here with the Euclidean distance and run this again, and then I suppose the plot you get is closer, even closer to the original PCA plot. But because Euclidean distances is what you see in, or what you get with PCA, because it's sort of sum of squares. But we will in the exercises have a look at some very different, or some very sort of very different similarity metrics, and then PCOA may give a quite different result.